Bismillahirrahmanirrahim. In our today's lecture, we'll talk about plastic equilibrium in soils. And to make it sound a little easier, you can simply say that we will see that how a soil behaves behind a retaining wall. And from our previous knowledge, we know that a retaining structure is, as the name suggests, is a structure that is retaining something, and for our case, it is retaining some soil. So generally, if I talk about our topic, so it will be something looking something like this, that we have this is a concrete wall or maybe made of some other material, and this is a material that it is retaining, that is preventing from falling it. Okay. So before we go in detail, I would like to show you some videos. I think when we see the videos first, then I'm sure it will be quite easier to understand. So first have a look at this video first.
Retaining wall failure, a familiar hazard in ground engineering. An engineer designed a wall to hold the dry sandy soil whilst houses have been built above. Examples of this can be seen where roads or railways or other excavations have been built that cut into the land. Unfortunately, this wall has not been designed correctly and has started to fail. This slope failure is translational in nature, and you can see the slip planes that have formed. Slope failures in wet clays and silts tend to fail at shallower angles and be of a rotational or flow type failure.
So there is another video that's similar to this one. So you see here, please understand this right now, that it says active condition. We'll talk about in detail that what is an active condition, but for now just have a look at this. So this was the active condition, and then we have the second video here that is about, just have a look at it. For some reason internet is a little bit slow today. Okay, let's see. So it says passive condition. So the first thing that we saw, the first video, that was active condition, and this is now passive condition. Alright, so we have just seen two videos, and in both of the videos the first video was about active earth pressure, and the second one had both active and passive earth pressure. So just to explain this, so if this is the retaining wall and this is the soil mass that is being retained behind the retaining wall, so this is the soil. Okay, so before I go in detail, let me make it a little easier. Let me just ease that up for you so it's easier to understand. So for instance, you can imagine that we have a ground surface. Okay, so this is the ground surface, and we are making an excavation. That's a big excavation, let's say maybe 10 feet deep, and maybe 10 feet wide, you can say. So what we are going to do is that we are removing the soil from here. We are excavating it. So that means that there is soil here and there is soil here. This all is soil. And what we have done is that we have removed the soil from here. Now the particles that were there already, they were all in equilibrium condition. Okay, nothing was happening. Now what's going to happen is that all the soil that was here, that was supporting this material, now that is gone. So now you can imagine what will happen. To retain its equilibrium condition, this is going to fall inside. This is going to fall inside. And to prevent that, what we are going to do is that we are going to make a retaining wall. So let's say I made a retaining wall here and the retaining wall here. So what that retaining wall will do, it will give support against this pressure. So this pressure here that is making the wall fail inside the excavation is called as the lateral earth pressure. So to understand lateral pressure, different theories have been put forward. The first one was by Coulomb and the second one was by Rankine. So Rankine's theory is the mostly used one. Okay, so according to Rankine, let's talk about this one here. So he says that whenever a situation like this here is there, that a wall is retaining a soil behind it, so there are two kind of condition. Actually there are three, but according to Rankine, he says first one is active state, we call it as Rankine's active state, and the second one is called as the passive state. So in active state, let's see what's happening in active state. Let me remove this portion and we just consider this one single portion here that is retaining a soil here. Okay, so if this lateral earth pressure is trying to push the wall outside, so there is a chance of tilting of the wall. Okay, if a thing like this is happening, okay, so this is called as an active case. Okay, but on the contrary, if a situation is like this, that this is the retaining wall and this is the soil behind it, and this time the retaining wall is trying to move inside, it is pushing the soil inside, so that is called as a passive case. So passive case, so here the wall is pushing inside. So you see the difference. In active case, wall is moving away from the soil, and in the passive case, wall is moving towards the soil. Okay, so so Rankine, to see Rankine, he says that he explained these certain terms, and that let's have a look at it. So he said that first, okay, so once again we have the situation here. Let me draw the wall here. So this is the wall, this is the retaining wall, and this is the soil mass. This whole is the soil mass. So if we consider any element, for instance we have considered this green element here. Okay, so the vertical stress acting on it at a certain depth z is indicated by sigma z, and we know that that is equal to gamma into z, that is unit weight of the soil into the depth at which we are measuring the stress. And similarly, sigma x is the pressure exerted in the horizontal direction. Basically in Rankine we are considering soil to be in two dimensions, so that's why we have only sigma z and sigma x. In real life we know that there are three-dimensional stresses, but for our understanding and for making things easier, as were done by Rankine, so we consider only two dimensions. So that's why we have a vertical stress and we have a horizontal stress. So according to Rankine, he says that there is one thing that is called as coefficient of earth pressure at rest. It is indicated by K naught, and it is equal to sigma x over sigma z. So sigma x over sigma z, that means horizontal stress over the vertical stress, and this is for a natural situation. Okay, sorry, so this is for a natural situation. If the natural process of deposition, once the soil was placed in history, so it was deposited, and at that time the soil was in a condition of K naught condition or an at rest condition. So in that conditions it is simply equal to horizontal stress over sigma z, or the vertical stress, and we can find sigma naught. There is a certain formula, 1 minus sine phi into root OCR. OCR is over consolidation ratio. If you have a normally consolidated soil, you have an OCR of 1, and if it's a sandy soil, so naturally it remains 1. So you only have to plug in the value of phi. Okay, so in this way you can find out K naught value. The second thing, as we have explained earlier, so according to Rankine, active earth pressure is indicated by Ka, and once again it is equal to sigma x over sigma z, that means horizontal stress over the vertical stress, but this time you see it's equal to minor principal stress over the major principal stress. So let's see why do we have this situation here. So previously in our last classes, in the stresses class, we already discussed the principal stresses. So we do not see any shear stresses on this element. if we talk about this particular element, so you see there are no shear stresses acting on the planes where sigma z and sigma x are acting. So that means these are the principal stresses. Okay, so we know that always one is a major principal stress and the other is a minor principal stress. Okay, so in active condition our formula remains the same, that sigma x over sigma z is equal to the coefficient of earth pressure, but it becomes active once the horizontal pressure is the minor principal stress and vertical pressure is the major principal stress. Okay, and on the contrary, in the passive earth pressure the situation remains the same, that it is indicated by Kp and it is equal to sigma x over sigma z, that means horizontal stress over the vertical stress. But this time you see here that major principal stress is now the horizontal stress and minor is the vertical stress, that is equal to gamma z. So now let's have a look at this. So we just learned that k naught is equal to sigma x over the sigma z. If we talk about this element here, sigma x is the horizontal stress and sigma z is the vertical stress. In active earth pressure condition, so just to jog your memories, we know that this is the vertical wall, so and this is the soil behind it. Okay, so if the wall is moving away, okay, let me use a different pen so it will be easier to understand. Let me rub this up. So if this is the retaining wall, okay, and this is the soil, so and this is the element that we are considering, and this is sigma x and this is sigma z. So now that we know that sigma z value is equal to gamma into z, so that value will remain constant at a certain depth z. If this is the z depth, so at any different point or due to any condition, sigma z value is fixed. It's simply unit weight of soil into the depth at which you are measuring the stresses. So the only variation will occur in sigma x. Okay, so remember that sigma z will all remain constant. With the changing of the active to passive condition, only change in sigma x would occur. Okay, so now let's see. So in Ka, active earth pressure condition, we said that sigma x over sigma z, we said that now in active case this is the minor principal stress and this is the major principal stress. Now how did that happen? So let me rub that again and make a bigger picture actually. Just a minute. So this is the wall, this is the soil and this is the element. So now what happened, that we said that in active case wall is moving away from the soil. So you see that once we have this soil wall moving away, so that means there will be relief in the horizontal stress. You see here initially particles were tightly packed here, but as the stress is relieved, because you see this is the gap here being produced, so the soil will naturally move here, it will start to move down. So that means there is reduction in sigma x, whatever, because sigma z is constant, we already discussed. So there is reduction in sigma x because the soil is now has free space to move. So that means the confinement, the adjacent particles that were there, adjacent elements, so now they are at a distance, they are at a relief now, so that naturally this value would go down. So that's why sigma x is indicated as minor principal stress and sigma 1 as the major principal stress. To explain this once again, we have a look at this video here. So you see here in active earth
This
condition,
is an example of a retaining wall failure.
for a while. So in active earth condition, you see here this wall is moving away from the soil. So this was the soil and this, and now you see that there is relief here because there is more space, so that's why the wall is moving away. So sigma x or the horizontal stress is being relieved. Okay, so same thing we just learned here, because the wall is moving away, so we have relief in the horizontal stresses, so that's why horizontal stress becomes minor principal stress and the vertical stress becomes the major principal stress. Now on the other hand, once we are talking about the case of passive earth pressure, so in passive earth pressure, Kp is equal to once again sigma x over sigma z, that is horizontal stress over the vertical stress. So this time this is equal to sigma 1 over the sigma 3. That means now the horizontal stress is the major principal stress and sigma 3 is the minor principal stress or the sigma z. So in this case this is the wall and this is the embankment, but now what's happening, wall is moving towards the embankment towards the soil. So that means the particles that were already there, they are now more compressed. So once they are more compressed, so that means there is more horizontal stress because there's a push from this side. Okay, so that's why horizontal stress becomes the major principal stress and the vertical stress becomes the minor principal stress. So this is how, this was the about coefficient of, we call them as coefficient of earth pressures. Okay, so K naught is the at rest value, at rest, Ka is the active condition, and Kp is the passive condition. So we have three values of the coefficient of earth pressures. So we have already seen, so you can the formula is for sandy soils. This is, please remember that this formula is for sandy soils only, that is equal to tan square 45 minus 5 by 2, and passive is equal to tan square 45 plus 5 by 2. We will get to its derivation in just a minute. So here is a general comparison. You see here, at rest condition is K naught, this is the value, and then Ka value is lesser than K naught, okay, and then Kp value is very large value. So the soil is compressing here and soil is in expansion here. Okay, so here is a comparison. So K naught value, for example, it's not really fixed. If K naught is, let's say, 0.7, then Ka will be maybe 4 and Kp would be maybe 1.3. So this is a little comparison, but it's not necessary. It can be anything, but this is how the values would change from each other. Okay, so now let's see that how Ka is equal to, or Kp is equal to tan square 45 plus 5 by 2. So here is a little derivation here. So near to this Tyrannosaurus playing the football, we have this graph here. So you see on x-axis we have the normal stress and on y-axis we have the shear stress. So we generally draw a Mohr circle. Okay, so in this Mohr circle, it is touching the failure plane, Mohr Coulomb failure plane. So the y-intercept is c. We know that this is cohesion, and the angle of this failure plane, this is the failure plane. So angle of this failure plane is phi dash. So we know that this value is the major principal stress and this value is the minor principal stress. I don't need to repeat that, we just discussed that in our stresses lecture. Okay, so from this figure we can say that so if this is the value d, so from this figure we can say that this is d. So sigma 1 plus d, so this value is sigma 1 plus d, this whole is equal to OA. So this is OA plus AB. So this is the radius of the Mohr circle, AB. So similar will be the value of here. So that's written here, OA plus AB. So it is equal to OA plus 1 sine phi. I'll come to that in a minute. We'll go now to see, have a look at this, sigma 3 plus d. So that means this value sigma 3 plus d. So this value here, so now it can be equal to OA, this is OA, minus this distance r radius, that is AB. So this is minus indicated here. So this is equal to OA into 1 minus sine alpha. Okay, how this is equal to OA 1 plus sine alpha? So let me come to that. So let me rub these drawings that I've just drawn. Oh, sorry. So sorry, just a minute. Okay, so OA plus AB is equal to OA plus sine. So what is AB? So if I what is the value of AB? If I consider this triangle here, so this is 90 degrees that you can see here. So this is phi, this is A, this is B, and this is O. So in this triangle, according to this triangle, sine phi is equal to perpendicular over hypotenuse, that is OA. This is perpendicular and this is hypotenuse. So from here I can say that AB is equal to, I can say that AB is equal to OA into sine of phi. So that value has been plugged in here. So this is equal to OA sine phi. This is also OA sine phi from the triangle OAB. So now you have taken the OA value common, so that's why we have this value OA 1 plus sine phi OA into 1 minus sine phi. So now what we do, if we divide these two equations, so dividing 1 by 2, so we have sigma 1 plus d is equal to OA 1 plus sine phi, sigma 3 plus t into OA 1 minus sine phi. Okay, so moving it here, so we have this situation, then multiplying sigma 3 with 1 plus sine phi and with d, we get this value. Okay, and then what happens? So now what we have done here, now we have shifted this d from this point on this side, so minus d. Now what we do, taking d common, so this will become minus 1 here if we take d common out of these two things. So this is 1 sine phi, and taking LCM, we are 1 minus sine phi to 1 plus 1 sine phi minus 1 plus sine phi. So now it trims down to this 2d sine phi dash of 1 minus sine phi. Okay, so now just a minute. So let me see, where is equation number 3? Okay, just a minute, let me see where I missed equation number 3. Somewhere here, just a minute. Oops. Okay, anyways, we will have a look at this. Okay, so now we have 2d sine phi 1 minus sine phi. So this has been, d has been replaced. So how the value of d is obtained? So let me go to this triangle. I think it's obtained from there. Okay, so from this triangle, let me call it as this E, and let's call this an F. So in triangle OEF, EF, so this portion here is cohesion, and this is D, and this is phi. Okay, so let's say, so tan of phi is equal to C over D. Okay, so tan of phi is C over D, so that means that D is equal to C over tan phi, and we know that tan phi is equal to sine phi over cos phi. Sorry, so I can say that from here, I can say that D is equal to C cos phi over sine phi. So let's see what there has been written for equation 3. So now we know that D has C into cos phi over sine phi. So we go back to our equations. So we learned that D is equal to C cos phi over sine phi. So from this formula, sine square phi plus cos square phi is equal to 1. We can say that cos square phi is equal to 1 minus sine square phi, and so that means cos phi is equal to under root of 1 minus sine square phi. Okay, so square phi, so that value has been plugged here. So that's why in place of this little d here, in place of this d here, we have this whole equation, that is c dash, that's effective cohesion, into 1 minus sine square phi that came from here, and over sine phi, we have already seen that. Okay, so now multiplying this, we will be 2c phi dash. So 1 minus sine square phi can be written as 1 plus sine phi into 1 minus sine phi, and we have a sine phi also on the outside. Okay, that is this one. So from this trigonometric rule, we know that a over under root a is equal to under root a. So this little fellow, this would become 1 minus under root sine phi. So we will be left with 2c dash 1 plus sine phi over 1 minus sine phi. Okay. So there is little correction here. I'm sorry, I missed it. This sine phi will be cancelled by this sine phi. So that's why we'll be left with 1 plus sine phi or 1 minus sine phi. So this does not come here. Okay. So that's why we are left with this equation. Sigma 1 dash is equal to sigma 3 dash 1 plus sine phi over 1 minus sine phi plus 2c dash 1 plus sine phi. Okay. So if I divide this equation with sigma 3 dash, okay, or basically if we convert it, we know that this is passive case. Okay, so if for c to 0 case, what will happen? This whole portion will become 0. So now we will be equal to sigma 1 dash is equal to sigma 3 dash tan square 45 plus phi dash by 2. We know that from trigonometry that is equal to sigma 1 dash equal to sigma 3 dash 1 plus sine phi dash over 1 minus sine phi dash. So you can also write it like this. Okay, tan square 45 plus phi dash by 2. Okay, and then sigma 1 over sigma 3, so that means major principal stress over minor principal stress, and we know that that was equal to Kp. Okay, because remember that Kp has very large values, so that means my major principal stress should come on upper side, and so that ratio is equal to Kp. So from here we know that Kp, the formula for passive earth pressure, is equal to sigma 1 over, sorry, why is it shift? Okay, it is equal to sigma 1 dash over sigma 3 dash, and that is equal to 1 plus sine phi dash over 1 minus sine phi dash, or tan square 55 plus phi dash. So whatever feels comfortable to you, can remember that equation. So this is for a case once we have c is equal to 0, and if we do not have a c is equal to 0, then we have to use this whole equation that we just derived, this one here. So we know that tan square 45 plus phi dash by 2 is equal to Kp, so we can plug in the values Kp, and this is Kp, and we know that for a passive case, major principal stress is the horizontal stress, so I can replace it by sigma h dash is equal to gamma z sigma, and then this is the vertical stress, so that is equal to gamma z Kp plus 2c under root Kp. So for a passive case, for a C5 soil, we have to use this equation. Okay, and for a active case, our equation will be naturally becoming equal to, you can derive that sigma h dash is equal to gamma z Ka minus 2c under root Ka. So it's your assignment that you have to derive that how for an active earth pressure case, Ka case, horizontal stress is equal to gamma z Ka minus 2c under root Ka. And for your easiness, I can say that Ka is equal to 1 minus sine phi dash over 1 plus sine phi dash, okay, or equal to tan square 45 minus phi by 2. 45 minus phi by 2. Okay, so you have to derive it yourself that how active earth pressure is equal to gamma z Ka minus 2c under root Ka. So this was all Rankines. We learned the derivation. So if you have any confusion, you can re-review the video, and plus all this has been provided in your notes. Okay, so according to Rankine, so we have seen this. Okay, all right, so according to Rankine, he says that this is from Terzaghis and Peck book, this image. He says that in Rankine's earth pressure, the failure plane would be at angle of 45 degree plus 5 by 2 from the minor principal stresses. Okay, the failure plane will make an angle of 45 degree plus 5 by 2 from the minor principal stresses. So we know that in active case, sigma h horizontal stress is the minor principal stress. This is sigma 3. So, and this is in horizontal direction, so that means from the horizontal direction the angle of failure plane should be 45 degree plus 5 by 2, and that has been shown here that from horizontal the angle is 45 degree plus 5 by 2, not only in this direction but also it can be in this direction, 45 degree plus 5 by 2. Okay, so this is the shear pattern that failure can happen in any direction. Okay, so if you go back to the video, so you can have a look at this, that this angle here, you don't know. Okay, let me copy that link here, just a minute. Copy. So just a minute, let me explain that to you. So we are opening the same here. Sorry for my internet, it's for some reason it's working very slow today. It will take a little while for the video to upload, but I just wanted to show you that how in real life, so you see here, let us go to the actual failure at this point.
Slope failures in wet clays and
So you
silts.
see here that this is the complete failure. So if I do the annotation here, where I do that, web capture. Okay. Okay, so you see here that this angle okay, so this angle of failure, oh god, what's happening? Just a minute, I don't know why is it so slow today. Okay, it's not useless. I have to use the snipping tool to make this understandable. Alright, so you see here this angle here, this makes from the horizontal, this should be 45. Sorry, let me where I can change the size. Okay, from here, so this angle is 45 plus 5 by 2 from the horizontal, because we know that this is active case, wall is moving away from the soil, so this is the horizontal direction, this is the sigma h. So here the failure plane is making an angle of, so this is the failure plane, this is red color, this is all the failure plane, so this is making an angle of 45 plus 5 by 2. So this can be anywhere, so all of this can be possible failure planes. Okay, and also we can have failure planes in this direction also. Okay, so they all make an angle of 45 degree plus 5 by 2, and this is called as the shear pattern. So we know that the angle of failure plane would be at an angle of 45 degree plus 5 by 2 from the horizontal, because the rule is, according to Rankine, that the failure plane will make an angle of 45 degree plus 5 by 2 from the minor principal stress. And for active case, minor principal stress is in the direction of the horizontal force. So, and in case of the passive earth pressure, we know that horizontal stress becomes the major principal stress and the vertical stress becomes the minor principal stress. So that means in that case this will happen. Now sigma v is the minor principal stress, so it will make an angle of 45 degree plus 5 by 2 from there. So if this is 45 by 5 by 2, then the remaining from horizontal should be 45 degree minus 5 by 2. So from horizontal surface, the failure plane will make an angle of 45 degree minus 5 by 2 in case of the passive earth pressure, because now horizontal stress is the major stress and vertical stress is the minor principal stress. Okay, so that's why we have a shear failure plane in this angle, that all these angles make an angle of 45 minus 5 by 2. Okay, so that has been explained in this figure here. Okay, so this is the stress diagram. If we consider this element E, okay, so at the bottom of the stress, sigma v will be gamma into z, okay, that is the vertical stress, and the at rest pressure is k naught gamma z, okay, because we know that formula for it is k naught if in at rest condition is equal to sigma x over sigma z, and that is equal to gamma into z. So for active case it will be equal to sigma x over gamma into z. So naturally horizontal stress in case of, let me change that to h, equal to ka into gamma z. So that has been explained here, ka into gamma z, that is the active earth pressure, and for passive earth pressure we multiply that with kp. So we will have, so this hash line tells us the limit. K naught is the rest value when nothing is happening, system is in equilibrium, and this is K naught value when system is in equilibrium. So you see here that horizontal stress is in much greater value than the at rest condition in case of passive earth pressure, and the value is reduced in case of the active earth pressure for the horizontal stresses. Okay, so the same thing is explained here. Now okay, so this is how we calculate the stresses. Now to calculate the force, because this is what happening there, because at the end of engineering calculation we end up calculating the force. We want to know that how much force is acting on the retaining wall. So if this is a retaining wall here, so I want to know that how much horizontal force, we call that as PA, okay, in case of active earth pressure, and PP in case of the passive earth pressure. So we want to know that how much force is being applied and at what location. Okay, so that is our major goal, because then we know that you also study structural engineering, so you know that based on your location of the force as the amount of the force, you design the reinforcement of the retaining wall. Okay, so this is the main purpose, to calculate the horizontal force. Actually previously we have been seeing the stresses, so now to calculate force, how will we do? So let's talk about this active earth pressure condition. So we have learned simply that horizontal stress, and once again just for you jog your memories, this is a C is equal to 0 case. Okay, and if I go back to the equation that we derived, just a minute, just a minute. So we, okay, let me draw it here. So the equation we derived was that horizontal stress is equal to Ka into gamma z. So this is being applied here. So because you see here z is changing, so that means the value of sigma h will change. So if this is the, let me use a darker color, so if this is the height of the retaining wall, so at the top of the retaining wall z is equal to 0, so that means sigma h will be equal to 0. So at this point we have z is equal to h by 2, so sigma h will be equal to Ka into h by 2 into gamma. Similarly at the bottom we will have gamma h is equal to Ka into gamma into h, that is the total height of the retaining wall. So we will end up having a triangular distribution. So this is what happens in case of an active earth pressure, that the stress distribution from the top of the wall where z is equal to 0 up to depth of the wall, but where z is equal to the depth of the or the height of the retaining wall, we will get a triangle. So to calculate the force, what we simply do is that we will find out the area of this triangle. So how we calculate the area? Half into b into h. So we know that half width is equal to gamma h into ka, that we have calculated, gamma h into ka, sorry, a should be small, gamma h into ka, and multiply that with the height of the retaining wall. So this way we will find out the pa value, and from triangle distribution we know that it acts at 1/3 of the height, so that is equal to h by 3. So similarly in case of the passive earth pressure, okay, we have the same formula, but only thing change would be that we will have kp instead of ka. Okay, so the area of the triangle will give us the force, passive force. So area of triangle is half b into h, half is gamma h into kp, and what is height? H is the height. So this is the height of the triangle h, and the base is gamma h into kp, as we can see from the formula here. So this is how we calculate the active earth force and the passive earth force, that is retaining, and once again it is acting at an angle at a distance of h by 3 from the toe of the wall. So this is the end, or we call that as a toe of the wall. So this is how we calculate the stresses and the amount of force that is acting behind a retaining wall. So after knowing this, you can decide the reinforcement or amount of failure that could happen. If the wall is not properly designed, okay, if the horizontal force is much greater than the ability of the wall to bear that pressure, so things like this can happen. We have a certain image here, you see. From the image you can see, let me zoom that up for you. So you see, this was the retaining wall in a circular fashion. So what happened? The amount of horizontal earth pressure that was coming from the land behind it was greater due to some reason, so this wall fell down. So if we do not design properly our retaining wall, once again here you see this was whole one wall, this whole up to here, and due to the wall not being properly designed, what happened? The active earth pressure forced this wall away, and this whole material fell off, and you see how hazardous is that if there's running traffic, so it can cause a lot of danger. So this is how we will calculate, and this is how we design the case of the retaining wall. So you see here the formula here is very simple, because this is the case of a C is equal to 0 soil, but we know that for a C5 soil our formula becomes little tricky. You have to remember this formula here, that in case of active case, formula is sigma h gamma z minus 2c Ka, and for a passive case, sigma h equal to gamma z Kp plus 2c Kp. And we know the formula of Ka is 1 minus sin phi 1 plus sin phi, and Kp is equal to 1 plus sin phi over 1 minus sin phi. So whenever you're doing a numerical, the first thing is always to find out the value of Ka if you're dealing with an active case, and a value of Kp if you're dealing with a passive case, for a passive case. Okay. So okay, what else are we? Okay, so now we will see depth of unsupported excavation in clays. Okay. Okay, so if we have clay soil, then we want to know that how much depth we can dig in vertically. If this is the clay soil, so we want to know that how much deeper we can dig in inside the soil, okay, so that it does not fall in automatically, and we do not need to provide any retaining wall. So that is called as the depth of unsupported excavation in clays. So for total active pressure, that means this horizontal force, because if there is this active force, that means it will make the wall fall inside the excavation. So if this force is 0, that means the wall is going to be stable, and there will be no force that will be pushing the ground inside the excavation. So based on that, we can say that Pa is equal to 0, and we know that the formula of Pa for a C5 soil is half gamma z square Ka minus 2c z into Ka, and that is equal to 0. So okay, before that, I missed one step actually. We should first see how to convert the stresses into force. We just learned to convert the stresses of sea soils. So here is this case. Let me zoom that up. Sorry. So in case of a C5 soil, the method of calculating force, active force and passive force, will be by drawing this diagram. So this is the retaining wall, and behind the retaining wall we know that the depth of retaining wall is Z. So the cohesion portion remains constant, okay, and that is equal to 2c under root kp, okay, and the kp gamma z portion is the variant, because z is increasing. At the top value z is 0 and at the bottom z is equal to z. So as the value of z is increasing, so does the value of this portion increases, okay. Cohesion remains constant for one clay soil, so that's why 2c under root kp remains constant, okay. Let me, this is the passive case, so just I'll write that equation here. Sigma h is equal to 2c under root kp plus kp gamma z, okay. So this remains the constant value throughout from top to the bottom, and the second portion is changing. So now this whole figure here, we will use this whole figure here to calculate the total active earth pressure that is acting behind the retaining wall. So what we are going to do is that we are going to find out the area of this rectangle plus the area of this triangle. So the area of rectangle is 2ck under root kp is the width and height is z. So 2ckp under root z. So this is the area of the rectangle, and this is the area of the triangle. The base is kp gamma z, 1 by 2 and z. So 1 by 2, z is the height and this is the base. So after multiplying, we get the situation that total passive force in a C5 soil is equal to 2c z under root kp plus half, these two multiply, z square kp into gamma. So this is the total amount of force that is acting behind the C5 soil retaining wall passive case. And in active case, we know that the formula for active case was 2c under root ka minus ka gamma z, okay. So the second term was in subtraction. So what we are going to do is that 2c under root ka remains constant. This is this whole triangle. The width is 2c ka and the height is equal to z, total z, and this minus gamma z ka, that means we have to subtract this portion. So this should be subtracted. So this triangle will be subtracted from this. So what we do is that we find out the area of this of the rectangle first. So the area of rectangle is, so this is PA, area of rectangle is 2c under root ka multiplied by z, because this is the area of the rectangle, minus the area of the triangle, so minus half. So the total width is gamma z ka into z. So this whole is gamma z ka, and this whole height is z, and 1 by 2. So we are subtracting this. So let's subtract 2c z under root ka minus half gamma z square ka. Okay. So in active case, okay, I did, just a minute, I guess, oh my bad, I did this wrong. Let's go back to the equation. I'm sorry. So in active case, minus cohesion is in subtraction. This is sorry, please correct this. I don't have to re-record the lecture, so I'll do correction here. So many apologies for. So this portion, I'm sorry. So in active case, PA is equal to gamma z ka minus 2c under root ka. I'm sorry. Okay, so the area of the triangle will come first. So that is area of the triangle, gamma z ka into z, and then the area of the rectangle, 2c ka into z. So this will lead us to this value of the active earth pressure. half z gamma z Ka minus 2c Ka into z. Okay, so this is how we calculate the active earth force behind the C5 soil retaining wall. So that thing was explained here, that for an unsupported excavation the Pa value should be 0 because there will be no force that is pushing the ground inside. So naturally this value should be 0. So that means once we put this 0, so this portion moves on the right side. Half gamma z square Ka is equal to 2c z Ka, and then bring the let the z's remain here, so this z cancels out, so that will equal to 4c over Ka under Ka, and according to the previous rule we just saw, we are left with this equation. So finally we can say that z is equal to 4c over gamma Ka. So this means at a depth of z, we call that as zc, critical depth. So at a depth of zc, that is equal to 4 times cohesion over gamma under Ka, we will be able to make a vertical cut in a C5 soil without generating any active earth pressure. That means we do not need to provide a retaining wall, and we can do a foundation work or any kind of work without providing any lateral support to the ground. So if we have a purely cohesive soil, that means sigma phi is equal to 0, that makes K is equal to 1. So this is for a purely cohesive soil, critical depth is 4c over gamma. Okay, so this is how we calculate the depth of unsupported excavation in a purely cohesive soil. Alright, so one important thing to remember is there that whenever we are doing calculations, we should remember that we have tension cracks in case of the cohesive soils. Whenever there will be cohesive soils, we will have tension crack generated in them, and to see that up to what depth the tension cracks would go. Okay, so we can say that from the equation of the active stress, we know that sigma A is equal to gamma z Ka minus 2c Ka. So active pressure will be positive once this value is larger than the value of this, because if the second term becomes larger, so value will be negative. So that means until gamma zk is greater than 2c under root Ka, we will have a positive value of the active earth pressure. And because we know that if the value of active becomes negative, so that means the soil is in tension, and eventually because soil cannot resist tension, so that means there will be development of the tension cracks. Okay, so based on this, gamma z Ka should be equal to 2c under root Ka. Shifting gamma K on the other side, we are left with this equation, z is equal greater than 2c over under root gamma A. So unless our depth of excavation, okay, sorry, up to a depth of 2c under root gamma Ka, we will have a tension crack. So if our depth is less than 2c under root Ka, there will be negative earth pressure, and that means there will be tension cracks. So to explain this, if this is a retaining wall and this is a C5 soil, so that means up to a depth of ZC, that is equal to 2c Ka, up to this depth we will have tension cracks. Okay, so up to this depth where there will be tension cracks. So this is how we calculate the depth of the tension crack, that 2c over gamma under root Ka. So this was pretty much all about Rankine's earth pressure theory, which considers both the active and passive cases, and we learned how to calculate the force in case of active and passive conditions. And one important thing is that if you are working under water table, then you simply replace, while you're calculating gamma, you replace it with the gamma submerged value, that is gamma saturated minus gamma W. Okay, while calculation of gamma Ka, so we will replace under water table gamma with gamma dash. So the one thing I left is that there are assumptions in the Rankine's earth pressure theory. So let me have a look at the assumptions. Okay, Rankine's assumption says that soil is isotropic homogeneous, backfill is horizontal, wall is vertical, and wall friction is neglected, and failure is a plane strain problem. That means that failure will happen only in 2 dimensions that we are seeing in our figures. So these are the assumptions of the Rankine's theory. So we are neglecting any friction between the wall and the soil, but in real life we know that there is always friction present. So if we consider friction present, then our failure plane, previously we are seeing that all the failure planes like this one, they are totally in two-dimensional. They are not curving, they are only a single line failures. Okay, we call that as plane strain problem. But if we consider friction, then you see we have a curvature or hyperbolic failure planes. This happens once we consider the roughness of the soil and the friction between the retaining wall. But it's just for your understanding. We do not have to go in detail for the rough wall, but you should know that in pure Rankine case, this is the retaining wall, then the failure plane will always be a vertical, and we already know that for active case this will be 45 degree minus 5 by 2, and for a passive case it will be equal to 45 degree plus 5 by 2, but it will always be vertical. But if in case of rough walls, because we are considering for Rankine smooth walls, and by smooth walls we mean that there is no friction between the wall and the soil, but in real life there is roughness, so we will end up having curved wall failures, curved failure planes. Okay, so that's it for today's lecture. So if you have any questions, we can discuss them in the lecture. So it's a good idea to go through the whole video and understand it well. Assalamu alaikum.